Okay, so this week we're gonna start with chapter 11, reference planes. So this is just an overview. So when you think about a linear measurement, it always starts at a reference point, okay? Because we're doing a measurement, you're measuring anyway from this point all the way to here. So your measurement is from here to there, so therefore the end point is your measured point. So these reference points are usually on a plane, okay? So here the dotted line is your reference plane. So we're going to study about these planes, how we make it, okay? And we also call them surface and surface plates, so it's the same thing. Alright, so this guy, he lived from 1803 to 1887. He's a Joseph Whitworth, Sir, title. So he was a major factor in manufacturing and machining, British, of course. So he applied new technique in which he used his understanding of the importance of accuracy in the machining process. So what he understood was that precision manufacturing, okay, they definitely need precision measurement. So you can do precision manufacturing without having a precision measurement. So therefore the precision in measurement is very important for manufacturing. He is credited with the invention of three-plate method. For that's nothing but just we're producing the flatness by using this method. He also discovered huge masses of metal, okay, did not ensure the strength or stability, meaning like even if you have a gigantic mass, okay, that's not going to give you strength or stability. It's the structure that gives you the strength and stability, okay, not the size or the mass. Okay, so for us to be able to make the reference plane, we definitely need to understand the flatness. Okay, so flatness is the evenness or levelness of a surface, and it is the degree to which the reference plane corresponds to the theoretically perfect plane or the surface plate. So if you don't have a good surface plate, okay, to put your part to measure, even if you have a really good height gauge, you're gonna lose the accuracy and precision if you don't have a good surface plate to put your part to measure it with this whatever sophisticated instrument you would use. So the flatness of your surface plate is incredibly important. So if you think about the flatness, we call these surfaces the datum planes because you put the object to be measured on these surfaces and get the data or values, so therefore we call that datum planes. And flatness in nature, okay, it does not appear in the natural world because flatness is entirely developed in the manufacturing world with industrial revolution. Because if you think about the world, you can't be able to name, okay, one thing that has a perfect flatness. The nature doesn't produce any of that, okay? So this completely man-made. So another guy, Richard Roberts, he lived in 1817 and he invented the first machine, planer, right there. So that can develop the flat surfaces. And this is how we make the surfaces that we need for measurement. Okay, so another thing you have to know is your degradation of workmanship. This is just a principle and it's a very vital step in metrology's progression to its current level of development. So you definitely need to know this principle. So in this principle, we're looking at the products. They're not as precise as the machines. And the machines are definitely not as precise as the gauges, and the gauges are not as precise as the standards. So you can take a look at it here. So that's how we usually calibrate, okay? But then we always think that they're not as precise to each other for each step that we go towards our mother standard right there. So therefore, the most accurate work can be obtained without even using the standards or previously manufactured parts to compare to. So that's a very strange thing, but then also true, okay? Meaning that we can be able to develop a better product without even using it against the standard. And yes, you can. So in manufacturing, plain surfaces without previously manufactured items should be capable of perfection. So that's how we believe in it, okay? Therefore, you can even be able to make products that are better than the standards. And that's the only reason why you can update the better standards, because you're making a standard that is better than the current standard. So making, in manufacturing, it is possible to upgrade that perfection, and you don't really need to compare to the standard. So that's what it's talking about. So in other words, a plain surface with high order of accuracy can be developed without having a standard. So this truism, okay, something that is true, which applies to all machine work. We call that degradation of workmanship. Okay, so the method, the 3-plate method. So we definitely have 3 plates here in this method. Is used to generate the flatness. Okay, we gotta make the surface, so therefore we will generate flatness in order for us to be able to make perfect reference plane. So it is used for practical problem solving, this method, in tool making, and also the machine construction. So when we make a machine, the machine is made of either metal or alloy. Okay, most of them have all surfaces, and most of them are flat. You also have curvatures, of course, in some machines. So in order for us to be able to construct a machine, an equipment or tool, we definitely use this method. So that's your 3-plate method. So when you take a look at this figure 11.3, we have 1, 2, and then 3. And this is prior to scrapping, okay? It's just an exaggerated picture. So this is showing that the possible surface conformation of these 3 plates after finished machining, okay? So not very good because we're exaggerating it so we can see the surface. So you can't really have high precision on the flatness right here. The second step, so that's your first step in the method. So what you do, so this step is nothing but we're using 2 plates out of 3 to see if they agree. This is an exaggerated picture, so you can see the surfaces, they're not very good, okay, because they're not flat. So therefore the agreement is not perfect. So that's what we're doing here. And then step 2, the same thing. At the completion of this step, both number 2 and number 3, so this is number 2 and then that's number 3 and that's number 1, will have picked up number 1's error. Okay, so we're gonna put 3 on top of 1 and then check. We already did 2 on top of 1 and then check the surface. If they agree, then the flatness is kind of good. If they don't agree, then we have to do more, okay, on sliding these two parts. So right now at step 2, and we call that the control plate, which is your 1. This is not the control yet, we're just checking, okay? So step 1 and step 2, when you pay attention to that, you're going to see step 1 is the plate number 1 is not yet in control. So right now we're checking the second plate, which is your third. We already did that right here in the step 1. Now we are going to call this plate number 1 the control plate. Again, we're finding agreement between the two surfaces. Up to step 2, none of them is known to be flat, okay? Okay, we're going to continue scrapping. So I have number 1 right there, and then I have 2, 3, and then 2, 3 right there. This is before scrapping. See how the surfaces are aligned. So by scrapping some of number 1's error off of number 2 here, okay, and some off of number 3, we get closer to flatness for these tooths, okay? So you continue to step 4. Here again, we don't have any control plate in step 3. In step 4, we have number 2 as our control plate. Again, you're trying to find better agreement between the two plates. So at the completion of this step, so this is after scrapping and that's before scrapping, just like the step 3, the plates may be of approximately the same flatness, but one is convex and the other one is concave, okay? So when you take a look at it here, concave, and then the other one is convex. Here is a pretty bad, that's before scrapping, this is after. But then you still don't have the flatness, okay? So all are of about equal flatness right now. But then they have a little bit of curvature, right? Step 5, we continue. So that's before scrapping and this is after. None of them is in control plate. After scrapping, we look at the agreement again. So the first time, plate number 1 and number 3 were brought together. So what we're doing is we're scrapping 2 plates at a time and rotating it, okay? So that's what you see. So only number 3, okay, was scrapped right here. So this time, both of them, so 1 is scrapping with 3 and 2 is right here. So by step 5, 1 and 3, they are flatter because the surface is in better agreement than 2. 2 come from your step 4 and it still have a little bit of curvature right there. Now we go into step 6 and we're going to choose 3 as your control plate. This is before scrapping. So here see, still we have a little bit of curvature. 3 has a better flatness. So we're going to scrap, scrap, scrapped, and now 2 loses its curvature. So 2 becomes flat. So 1 and 3 and 2, they're all in agreement. Okay. So although this step brings the 3 plates into approximate agreement, it does not mean they are flat. They just look flat. So we're talking about the precision and the accuracy here. How sophisticated or fine, alright, these surfaces are that you have to be so careful about your workmanship, your scrapping, by the way. So the entire procedure is repeated again and again until the desired flatness is obtained. Okay, Japanese, they are very good at this. I don't know why they kind of are well known as a perfectionist for the Japanese gene, because everything they do is incredibly perfect. Whatever they do, I don't know why, except looking good or not, I guess. Oh gosh. Okay, perpendicularity. So perpendicularity is an important reference. So this is another thing that we are studying for surfaces. Okay, so that's another important reference, which is just a right angle. Right angle is nothing but your 90 degree, which is like this. So unlike flatness, we're gonna need 180, I forget the degree here, degree angle, called a straight angle. And that is your 180 degree angle to generate a right angle. So in order for us to be able to generate a right angle or perpendicularity reference plane, we have to start with 180 degree angle, which is just a flat surface. And that's where we use a flat surface to make perpendicularity. So therefore, the right angle will always contain error from the straight angle. So meaning, since the right angle is generated after we build this 180 degree surface, so everything that we make error in making 180 degree surface is going to affect the right angle. Okay, so the error is, as you know, you can pass the error from one instrument or one object to another. Okay. This is just trying to tell you how we make the right angle. So same as your surface, we're going to start doing it by agreement in between. And we always choose a control. Okay, control is the one that you measure the other part agreement with it. So master squares can be generated by much the same technique as was used for generating plane surfaces. But the accuracy of the resulting square is dependent on the accuracy of the reference surface on which the generation took place. Okay, so here, step 3 and step 4, none of them, okay, neither square, we call this square. To make the right angle, we start from square. Is the contour square, and then you're going to scrap to increase the agreement between the two, okay, vertical surfaces. So after scrapping, you're going to get that. Then we're going to come back to number 1 and then do the scrapping again against number 2. Okay, so now your number 1 is in agreement with 2 and 3. So therefore you will get a perfect 90 degree, okay, reference plane. Now we're going to use the generation of squares again. If you use it on a curvature like this, okay, a circular surface, so they can usually pick up the error of the reference surface. So here, from here to here, definitely is a 90 degree because that's your square. But when you put it on a curved surface, okay, they will definitely pick up that error on it. So that's what we're talking about. It doesn't matter which part you use, 1 or 2 or 3. Okay, so here is your perpendicularity reference plane. We can also do the same thing and generate an inside square by using the same technique by scrapping. Okay, scrapping again and again, and then find the agreement. So we go from A and then B and then C and then D. So what we're trying to do is to make sure the inside square is going to be agree, okay, with your master square. That's just trying to tell you the error. So you have an error X, meaning like it's not in agreement with this, okay, master square right there. So therefore the inside square is not perfect. So that error, okay, is the error. It can be magnified all the way to 4x. Okay, so modern reference planes are generally, we use the materials they call granite instead of cast iron. Cast irons they're heavy and also they can be expensive. The granite surface plates American first used Granite for commercial surface plates around 1942. So there are different types of Granite plates. So we have here several kinds of Granite, several approaches to flatness, and various functional features like the ledges and the inserts. I'm going to show you what they are. So all you have to understand is Granite is definitely not just one type. It comes in different kinds. So therefore, we have to have different approaches to make flatness on Granite. So we can use this block, okay, as the reference plane because it's so flat, okay, and when you put the object, you can be able to measure it and increase your accuracy and reliability. So here is the types of Granite. So Granite surface plates accepts all types of stone surface plates. Granite is a stone anyway, so it can produce superior reference surfaces. So geologists divide stone into two groups. So the very first one is your sedimentary, and the other one is igneous. So sedimentary is they're formed, okay, from compacting your earth elements. So limestone, marble, slate, shale, sandstone, and all other stones, okay. And igneous is nothing but they're formed by cooling down and the solidification of molten earth. Okay, this is really hot. So when the molten earth cools down and solidifies, you're going to get this type of granite. So we have gabbro, we have granite, regular granite, and then we have diabase. Okay, so we have three different igneous type stones, and we sometimes call all of them granite. Sometimes we call by their name, okay? So don't get confused. And you're gonna see like granite, gabbro, granite, diabase. Sometimes you're gonna see diabase, gabbro, okay? And they mix them up because this is incredibly expensive. So this table is just showing you the natural surface plates material. So mineral constituents in descending order of abundance. You can see right here, one, and then two. So you don't really have to remember this table. If you can read it only one time, that should be alright. Okay, nobody's gonna ask you the whole thing. I just trying to introduce you the class of your granite and the color, and then the texture, and then the constituent of what they have inside. And this is just a minor constituents. Okay. So in descending order, and you will see the abundance. Okay, so once we've done with flatness, and then we did the perpendicularity, okay, for building the block, the surface plate. So after that, we're going to get into the stiffness. So stiffness is important when we measure heavy work pieces to close tolerance. So it measures the modulus. So every time we think about stiffness, you have to think about your physics, and that's we call that modulus of elasticity, okay, of the material, and just a material thing, and we call that Hooke's law. So I don't know you have already taken physics 1 or 2, so that's you definitely need to learn Hooke's law in physics 1, I believe, as far as I remember. So making a ratio of stress to strain. Okay, I'm gonna put a website for you to review, and you can also take a look into your physics 1 textbook. So stiffness is just a function of Q, okay, of the thickness in math. So therefore, we double the plate. So if we double the plate thickness, we increase the stiffness 8 times. Okay, why is it going to be 8 times? Go back to this modulus of elasticity, Hooke's law, and that's the reason why we get 8 for doubling up the thickness. So if we increase the thickness 26%, we double the stiffness. Okay, we can cut the deflection in half. Don't worry about the deflection test. So you just go with the thickness and then the stiffness. When you double that, double the thickness, you're going to get 8 times. So if I give you 26%, you want to increase 26% to 8 times. Okay. Okay, surface plate selection. You're going to choose a stone to make the surface. So strength versus wear represents a simple trade-off we face when we select the stone. Okay. So when deciding the stone type, we follow this standard. You don't have to remember that. But most surface plates, if you know it, that's okay. So you only try, I usually remember the GGG, okay, their genetic code. Anyway, so, but most surface plates from manufacturers exceed the minimum requirement of this standard, okay? In my time, we have to remember this. So what I did, I remembered that, and then I tried to remember number 3 right there. Okay. So anyway, so we usually look at cost and then loads, what you're gonna put on that surface. Okay, cost to make that surface, and all the surfaces need to be resurfaced. So you also have to think about resurfacing to decide which stone to select. So we choose less expensive dive-based and gabbro stones for cost and loads. And they can also carry heavy loads. For granite, we choose it when we don't want to do the resurfacing often, because this 2 stone, you have to do resurfacing. Classes and grades. So there are 2 classes of granite surface plates that are based solely on resistance to wear. So we have class 1 and then we have class 2. Class 1 being the highest wear resistance, and class 2 is just medium. Specification, then we divide these 2 classes into 2 grades. We have grade A and then grade B. Some of the company like this, they go by Granite AA grade. Okay, so grade A is for high quality precision work, and we use it in inspection. Then for grade B is for average quality precision work, and we use it in the toolroom or shop. Then this is the made in America, okay, Granite grade AA, and that's for laboratory use. So that's a pretty expensive. You have to pay about $500 to $600 for this little 36 inches by 36 inches by 6 inches block. Alright, so the production of surface plates. So granite surface plates allow us to measure to closer tolerances, and we can save money. So therefore, we usually choose this. So I've got one in my office. Therefore, we produce granite surfaces more than cast iron and steel reference surfaces. So the granite surface can be produced to flatness, so that can be measured in millionth of an inch at very low prices. So these plates also have great thermal stability. Okay, so those are the reasons why we're choosing granite over the other 2 stones. Okay, and then another factor that we consider is the hardness of surface plates. So when we select a surface plate, hardness is an important consideration. So here you will see a table. So this shows hardness values for Rockwell C test and scale row scope hardness test. And you can see right here is their values, okay? And you can also test for hardness using the scratch test and then Mohs scale. So here you have tail, gypsum, calcite. These are just the element type, okay? So what we do is we use these elements, okay, to test for the hardness. So hardness is the indication of wear resistance and high density. So granite can be run as strongly as metals. Okay, they can do that. You think like you can't you cannot ring the granite, but you can. So poorly finished surface would indicate the inability to ring to a granite plate. So if you want to check the finished surface, okay, quality, and what you do is you do a ring test. Okay, just ring it to the granite plate, and you can be able to identify if that finished surface is poor or not. Okay, I'm going to show you about the ledges. So thus we're considering the function, okay, of the surface. So ledges are the accepted part of the surface plate manufacturing. So every time you look at the surface plate, you're gonna see this little line right there. So that's just a narrow horizontal, okay, surface projecting from this little part right there, okay. They're not the same surface as first, and then this is second. So we call that ledge. So the grade of the plate is detected by its ledges. So for example, 2 ledges for inspection grade and 0 ledges for 2 room grade. So some people use the ledges to clamp on it, okay? But this type of clamping on the edge like that usually generate the clamping error, because edge clamping usually localizes the wear right there. Okay, we don't want the wear, especially on the surface plate, because they're very expensive. So if you want to eliminate using the clamp on the ledge, we developed something called threaded inserts. So these are your inserts on the surface, and you can use that, okay? So instead of doing the edge clamping, you can do clamping in these inserts. Care and maintenance. So here are the basic rules for surface plate use. You can just read it, okay? I don't want to read everything for you. I just trying to tell you to set the parts carefully on the surface plate. When you use it, dropping the parts onto the granite surface is going to chip or nick that surface. And then you're going to rotate the area of the surface plate used for inspection. Using the same area year after year can wear a hole in the plate, so you will definitely rotate the area. Just like you rotate your car tires, right, every 3 months. So when using the inserts, use the minimum torque, okay, required to hold the part in place. And don't place a heavier load on the table than the load rafting indicates. And so you can read it. So that's how you use your surface plate. And you don't have to put extensive care and maintenance for the plates. All you have to do is just do your regular cleaning. Okay, that's just keeping the surface clean, free from build up of dust, and this is what we don't want. Grease, grime, and all other foreign particles. Care and maintenance again, do not drop your wrenches and your hammers on the plates, because they can chip and nick off the surface plate. So therefore, do not use a granite surface at work benches where all your tools are. So make sure you check the surface plate regularly for wear. Check it by setting an indicator gauge. We have something called indicator to find the chips and nicks, okay, on the plate, and zero it on at any point on the table. So move the gauge on the plate and record the movements in the indicator to check your wear. So surface plates must be calibrated depending on the frequency of use. So if you use it often, to make sure you do regular calibration, okay, to check the wear. How flat is flat? So there's controversy around definition of flat. So here in this figure, this is just exaggerated drawings again, showing you the confusion about the flatness. So we do not use definition to generate flatness, because you can't use it. What we do is the configuration of your reference surfaces results from the method that generates, okay, the true flatness. So you just have to get on and make it. So here you can see if flat is smooth and even, these surfaces are flat, okay? And this surface is not smooth, okay? So you consider, is it still flat? Because you have the dented areas right there. But it looks pretty flat to you, okay, except this part. But don't confuse with the flatness. So if you look at it, even though you have a little bit of a curvature right there, that can be a good surface flatness. Yeah, this one too. Okay, so how flat is flat? So to define a plane, visualize it starting it with 3 points. Okay, you're gonna imagine, because there really is, we don't have a real flatness in the world. Like I said, in the nature, we cannot be able to produce a perfect flatness. You can only imagine. So why is that? So we're gonna go back to math. So to define a plane, you have to visualize it in your head, okay? You're gonna start with 3 points. So close your eyes and imagine 3 points in the space. So 1 point in a line and 2 lines, okay, that intersect. So one plane can have 3 of those points, and all of that 3 points got to be on that plane, okay? So since a line, we will go back to your elementary or middle school mathematics. So we have already learned a line is an infinite series of points. You should, as a university student, you should be able to see into the infinity and also see out of the infinity, and you have to practice that quite a lot in STEM major. About 80% of the student cannot be able to do that. 20% they practice and they can be able to do that, okay? Out of 20%, very few percent come with a natural inborn ability to be able to see that. So that depends on our genes. So anyway, every time you look at an object, you know that they are in a particular structure, the same thing as line. So line is a very simple structure, and each line, okay, is composed of infinite numbers of little points, okay? So they are, so you can put a line, draw with a lead pencil, and then suppose you put that on a microscope, and then we're gonna go zoom in, okay? We can go all the way, the most powerful microscope, and you're gonna see the lead breaks, okay? None of them is attached to each other. So what we see as something that is in a straight line is actually not in the reality, okay? So therefore, there's no absolute truth of everything that we know in science and everything that we know in the world that we're describing by using a particular language also is not the absolute truth. And so that's how we see in science about the truth. So anyway, so we're living in the middle. So here we go, back to the line. Line is composed of every infinite series of points right there. So now you can see they're gonna go forever, okay? They're gonna go forever to that side and then to this side. So now we have absence and then presence. So your plus and minus are nothing but, so whatever factor that you're looking at, we have something, if we think about the physical reality, you have something that you can be able to perceive with your intelligence, and we call that plus side. And that is also going to go all the way to infinity. Okay, and you have the minus side. Minus is not the reduction, okay, not like the mathematics. So in science, for physical reality that we're thinking about, you have a non-physical reality on the other side. And non-physical reality is just the absence of the physical reality, and we describe by minus, okay? Minus is not reduction in numbers like we do math in the world. Minus is just telling you the absence of that. So therefore, if this is a physical factor that you're thinking about, we do have the non-physical factor on the other side that you can see, which is going all the way to negative infinity. Okay, absence of physical world is also going all the way to the infinity. So if you think about things that are powerful, huge, you can only imagine. Okay, playing the same thing, there really is the most powerful, or the flat, the flatness, the most flatness in the world. If you want to get to the real absolute flatness, you can only imagine. So if we think about spirituality and religion, the same thing. We try to describe God as the best. Okay, someone who can forgive and who can be able to do beyond the ability of the human. So therefore you can only imagine, because that power is so great. The same thing as here, the absolute flatness, the power of the absolute flatness, the factor, is so huge that you can only imagine. Okay, we can't make it in a physical world. So that's how we see scientifically about any religion in the world. And try it. If you try to make the goodness at the most, okay, the highest level, you can't be able to find that kind of absolute, okay, ness in the world, or perfection in the world. You can only imagine. Okay, all right, so let's go back to here. The same thing, we're going to imagine, we're going to make a plane starting from 3 dots, and each dot is going to have a line. We will imagine the line crossing that, crossing this, and crossing that. And on these 3 lines, we're going to imagine a surface, and that surface is the flatness, okay, the absolute flatness you can only imagine. So each point could extend beyond the points that define it. So therefore points and lines here, which has no thickness, zero thickness does not exist, okay, in our world. Everything that you touch has a thickness. Okay, so which has no thickness are used when we define the plane. So the plane itself has no thickness. So since it is theoretical, this plane is the ideal reference plane. Everything that is ideal, everything that is perfect, everything that is the best doesn't exist. Okay, it's only in your head that you can imagine. Okay, so how flat is flat? In real world, we add substance to the theoretical perfectly flat plane. Okay, why? Because we want to see it in its physical state. So if we want to make the flat perfectly flat, okay, theoretically perfectly flat plane, in the reality, we're going to bring from the none or absence of, again, the minus going to the infinity. That is the absence of the physical thing, okay? So now we're going to come back to our world, the presence of the physical things that you can perceive. So that is what we're doing every time we make or generate the surface plane, okay, our reference plane. So now we're going to put the thickness into the imaginary perfect flat plane. So as soon as you put the thickness, you start to see it because you're making that with some sort of substance. Okay, so everything that is flat that we say in the world is not flat because it has some sort of, or some level of thickness. Okay, even the finest gold plate, you can eat it, right? Even that is not flat enough. Anyway, so therefore, every time we talk about surface flatness, we're making a purely arbitrary selection of the reference plane. Yeah. So therefore, we use a lot of virtual. So I want to teach you how to do your 3D so that you can be able to see that virtually. Okay. Again, the virtual world is the absence of physical or substance, again the material, but you can see the image. Okay, so our technology is that powerful as of today. So now we're going to get into figure 11 or 19. So this picture is just showing you the accuracy. Okay, must specify precisely how the accuracy is defined. So that means we can read on one surface plate at 0 deviation and x deviation 2x or even 4x. So this, okay, deviation depends on how you define it. So here you can see a lot of dents right there. Anyway, these are exaggerated surfaces. So if the highs and lows right there are average, this plate has, okay, perfect flatness. So here again, you have your high and then your low, and here is like so high right up there. So if the maximum deviation from the mean right there, you always have a mean, okay? If you have some sort of data. So if the maximum deviation from the mean is used, the same plate, okay, has a flatness of x if you use the mean. Then we're going to come into here. So if total deviation is used, the flatness become 2x. Here is a little gap, a little bit bigger, and then here is so high, yeah? So now if 1 point varies, does that make the expression of the flatness double? It does. So here, look at that. These are all average, high, and low, and all of a sudden you have a really high thing right there, okay? And that's like 2 times of what we have here, the total deviation, okay? So anyway, all you have to understand is your accuracy is how you define it. Okay, so this is our last slide. So yay, in our federal specification, they state that no point may deviate more than the specified tolerance from a mean plane. So your tolerance widens as the size increases. So when you take a look at it here, we have size, and then we have accuracy. So here you have your size. This side is your work surface accuracy. So when you look at your work surface, you have your length and then your width. Okay, that's your regular 2 dimensions. And these are your inches. I'm just showing you the measurement of the length and the measurement of your width right there. Okay, then it's going all the way down, increasing. And when you read, okay, something, you don't have to just go line by line. You scan it. Okay, so that's how you also save time in your test. And scan through the table and then see the trend. Okay, see the trend is nothing but how it's going. Is it going increasing or decreasing? Okay, and then check the all of that measurement units. Yeah, so here grade A thickness, we have minimum going all the way down. Grade B, your thickness increasing. So every time you see increasing, by looking at that column, you know that the sizes is going up. Yeah, grade A, and then tolerance. Okay, that's your range specification. It's going from here. Again, grade B, tolerance, the same thing. So the grade A has a tolerance, a smaller tolerance when you compare to here, because when you look at the decimal, look at the decimal. See here, 1, 2, 3, 4, 5, 6. This decimal is 1, 2, 3, 4. Yeah. So therefore, this tolerance is bigger or larger than this one. So therefore, grade A is better. Yeah. Okay, that's it for chapter 11, and we're gonna go to chapter 12 on Thursday. And make sure you do your assignments. Again, how to study as a university scholar. You have to read the handout. If you don't want to read the handout, read the entire textbook. So you can do one or the other thing, but this is your responsibility to read. So first thing is you read, and then you listen my lecture. You can pause it, you can continue, pause it, come back to it, whatever you want to do, depends on your time, okay? And I am spending so much time for making this for you, so make sure you use it. And then you're going to read your presentation, okay, PowerPoint. So there's a PDF for PowerPoint. So that's just extracting the key points, okay? Your handout, read it. Your presentation, read it. Listen to the lecture. And then do the assignments. And then you're going to do that again. And I already put the multiple choices and the short answers. So chapter 9, 10, 11 is already there, and make sure you study those MCQs so you will be ready for your final. Okay? Alright, so that's it for chapter 11.